Hello, I'm an academic from Griffith University, and I'm sharing my journey to relearn organic chemistry after being focused on other fields for, almost 15 years. Today we're going to talk about trends in chemical bonding. There are multiple factors that influence chemical reactions, but the main three ones are steric effects, electronic effects, and the often somewhat neglected stereoelectronic effects. So we'll look at the easiest one to understand first, and that is steric effects. Steric effects come down to the structure of the chemical itself. Larger functional groups impact the degree of conformational freedom that molecule can adopt and essentially block chemical attack from other molecules. Sterics therefore affects the rate and reactivity of chemical reactions. So if we have a look at the reaction scheme, we've got what looks like a DNA base pair with two nucleophilic alcohols, and these are going to attack an electron-deficient carbon at the center of this protecting group. Now, we're dealing with weak nucleophiles and a relatively mild base of pyridine, so this is probably going to be an SN1 reaction that occurs in two steps, where we first get elimination of the chloride leaving group, creating a carbocation, followed by nucleophilic attack. If we assume this is an SN1 reaction mechanism, first step is going to be elimination of this chlorine as a chloride. Once that occurs, we've got an electron-deficient carbon that's lacking the two electrons stolen by the chloride. This makes this central carbocation extremely reactive, but as you can see, it's flanked on all three sides by three aromatic rings. So while the central carbon really wants electrons, the nucleophile that's going to deliver them needs to be able to thread the needle between those three large groups. These three large groups are guarding that central carbon, preventing very large nucleophiles from accessing it, or at the very least slowing them down considerably. So if we take a look at the nucleophile, there are two nucleophilic alcohol groups shown here. One's a primary alcohol, the other is a secondary alcohol. Now there's no particular difference in terms of how nucleophilic they are. However, because one's a primary alcohol and the other is a secondary alcohol, the reaction comes down to how easily these alcohols can access the carbocation trapped between these three large aromatic groups. So here the two transition states have been visualized. We can see we have our carbocation with its empty p orbital shown here. We also have our two potential nucleophilic alcohols with an electron-rich lone pair oriented towards the carbocation. However, only one of the alcohols, the primary one, benefits from a lack of steric clutter. So we can see here that the alcohol group's essentially thrust out. It's kind of like the molecules giving a handshake out to the carbocation. Whereas looking at the secondary alcohol, we can see that there's this furan ring and it's bumping into or clashing with the aromatic groups near to the carbocation. So the primary alcohol can get a lot closer to the carbocation than the secondary alcohol can. And indeed, for this reason, we see that 99% of the product occurs where the primary alcohol reacts with the carbocation, and less than 1% the secondary alcohol manages to get in there and react. Now looking at electronic effects. These can also impact the conformational freedom a molecule can adopt, as well as the rate and reactivity of chemical reactions, similar to steric effects. However, these occurs through inductive effects, which is through bond polarization, or through field effects, which is polarization through proximity or nearby space. So to give you an example of polarization through bonds, we can compare acetic acid, which has a pKa of 4.78, to trifluoroacetic acid, which has a pKa of 0.23, making trifluoroacetic acid 34,000 times more acidic than acetic acid. And the reason for this is electronegativity. So for trifluoroacetic acid, there are three fluorines attached to this carbon, and each of those fluorines is pulling electron density away from the carbon towards itself. That gives all of the fluorines a partial negative charge, and the carbon a strong partial positive charge, so it is deficient in electrons. To deal with that, the carbon draws upon electrons through this bond from this neighbouring carbon. It in turn does the same thing, withdrawing electron density from this oxygen towards that carbon. And finally, if we think about an acid, there needs to be a bond broken, giving off a proton. So in the case of trifluoroacetic acid, the electron density stabilizing the bond between the oxygen and the hydrogen is withdrawn to help stabilize the electronegative carbon nearby. So essentially, the effect of these fluorines is to pull the electron density away from this bond in blue in this direction. This weakens it, making breaking of this bond more easy to accomplish, increasing the acidity. This shouldn't be confused with resonance or mesomeric effects. So this polarization effect occurs through sigma bonds, whereas resonance effects, these occur through electron movement through pi bonds, that being the biggest difference between the two. These inductive effects can be felt over several bonds, so it's not just over neighbouring bonds. So if we look at a similar conversion of a methyl group to a trifluoromethyl group, we can see that these inductive effects occur over 1, 2, 3, 4, arguably 5 bonds before reaching the acidic proton. Another situation whereby inductive effects are really important for chemistry is stabilization of carbocations. So here we have a central carbocation. That carbon is extremely electron deficient. However, the more you surround it with electron-rich functional groups, the more stable that carbocation is going to be, because it can draw upon those functional groups to offset that deficiency. So this carbocation will be the least stable, but as we keep adding electron-rich functional groups, we're going to achieve a relatively stable carbocation shown here. And because it's partially stabilised, it's more inclined to form, making it a better precursor for SN1 type reactions. Keeping with electronic effects, now looking at field effects, this is polarisation of a molecule through space, not through direct bonds. If we take a look at these two molecules shown here, we're again looking at the acidity of the molecule or its propensity to give up that proton. Now you should see that there's a difference in the pKa between these two molecules, meaning that the molecule on the left is harder to deprotonate, whereas the molecule on the right is easier, making it a stronger acid. If we were to count the number of bonds between the chlorine atoms on this bridge, moving down to this acid group down here, we'd see that the number of bonds is the same. So 1, 2, 3, 4, 5, 6, 7, 8 versus 1, 2, 3, 4, 5, 6, 7, 8. So if it's not polarization through bonds, it therefore needs to be polarization through space. And we can see for the molecule on the left that the chlorines are oriented towards the acid group, whereas in the molecule on the right, the chlorines are oriented away from the acid group. If we think about deprotonation of this carboxylic acid, when that occurs, there's going to be a negative charge on this oxygen, and it's in closer proximity to these electronegative chlorine atoms. So that will create this sort of repulsive effect shown here. The same does not occur for the molecule on the right. So it's this repulsion or destabilization that makes the molecule on the left disfavored towards being deprotonated and acting like an acid. So these field effects, we can think about these in terms of the way that enzymes interact with substrates, or indeed molecules interacting with catalysts. You don't necessarily need direct bonding to enhance the rate of a chemical reaction. You only need close proximity and these field effects. And this holds great relevance for biology. Moving on to the often neglected final trend, which is stereoelectronic effects. These effects arise due to molecules being locked into certain conformations and orientations, often by electronic and steric effects, and these stabilize ground or transition states in the molecule, thereby influencing their reactivity. These are particularly important for pericyclic reactions. So we can look at the stereoelectronic factors influencing this E2 reaction, whereby we have a base, it's going to abstract one of the hydrogens at this position, giving us H2O and a bromide ion. Now, you might think that any number of the hydrogens adjacent to this bromine could be targeted in this reaction, but that isn't the case. Some are specifically favoured for attack by the base. Now we're going to focus on just two, the axial hydrogen, shown in this position, versus the equatorial hydrogen, shown in the same methylene group. One thing we saw in the previous slide is we need to form a double bond in this position. And if we take a look at the orbitals that would go towards creating this double bond, there is alignment for those orbitals in the axial position, whereas there is not alignment between the orbitals in the equatorial position. For this reason, the base favours the attack of the axial hydrogen shown here, and not the equatorial one shown on the right side. If we think about the transition state, the base will attack this hydrogen, which is going to donate its electrons into these orbitals shown here, while the electrons in the sigma bond to the bromine, they retreat to the bromide, completing the reaction. So the selection of the hydrogen by the base comes down to this proper alignment of orbitals, which we can think of as a steric decision governed by electronic effects. Now let's look at some different chemical bonding trends in tandem. First one we're going to look at is a tin-mediated addition of a propane group. Our starting materials are diastereomers, relating to the chirality of this carbon and the appended methyl groups. And we see that the reaction proceeds whereby we get loss of this acetate group mediated by the tin, resulting in addition of these propane groups, with the chirality of those groups influenced by the methyl groups on the opposite side of the molecule. First step of this reaction involves formation of the oxynium ion, like so. This gives us our reactive 5-membered furan ring. Just as a quick reminder of the conformers that you get from a furan ring, the two main ones are this envelope conformer, shown here, versus the half-chair conformation here. And you can see that the important location for transmitting steric influence over the molecule is here at this lip of the envelope. So the first thing we should think about is how might this oxonium react? We're not considering any of the functional groups around the ring, and there's really only two ways that a nucleophile can approach this molecule. Either from the inside of the envelope, so coming down in this direction, or from the outside of the envelope, coming up from underneath. And you might think, why is that? Well, much like our earlier example, we need to think about the orientation of the orbitals near to this oxonium group. So we have this double bond, there's going to be p orbitals associated with this double bond, and the nucleophile is going to approach to interact with those p orbitals. Now, only one of these approaches is favoured if we don't consider any functional groups nearby, and that is this inside attack pathway. And the reason for that is if we consider the outside attack and the two conformers of envelope and half-chair, if we look at the half-chair conformation, we can see that the incoming nucleophile is going to be eclipsed, meaning that it will be sterically impacted by the adjacent hydrogen atom. This steric influence is not present after inside attack, which makes this approach lower in energy and thus favoured. But what if we consider this chiral methyl group, shown here in green? So we've covered the stereoelectric component, which dictates that a nucleophile needs to approach either from the top or underneath, because that's the orientation of the p orbitals. If we now look at one of the methyl diastereomers, we can draw out the conformers, and we can see with the methyl group oriented away from the furan ring, the inside attack is favoured for the same reason as before. Indeed, if we look at the lower conformer, the methyl group oriented downwards is actually going to impact the approach of the nucleophile if it chose to come in via the outside route. So from this combination of stereoelectronics and sterics, this inside attack route is favoured when the methyl group is situated in this position. If you reverse that though, and place the methyl group in the opposite position, all of a sudden the inside attack route is going to be impacted sterically. So there's this clash between these two groups here. When you change the conformation like so, the methyl group moves away, and suddenly the outside attack route is clear for the nucleophile. And this becomes the reason whereby the orientation of a methyl group relatively far away from the active site can deliver stereoselectivity. Now, distinguishing between these two effects, be it electronic, steric, or stereoelectronic, isn't always easy to do or clear-cut. Just to give you one more example, we have an organometal reagent, so some kind of alkyl aluminate reagent. We have a chiral starting material with this oxygen projecting out towards us, and this guides the location where the aluminium will attack the molecule. So the lone pair of the oxygen will coordinate to the aluminium, and this is going to place this R group above this double bond here. Now, the reaction proceeds with the addition of two aluminium organometal reagents. The first one is positioned above the molecule here, so it's going to block arrival of the second aluminium reagent. So it's going to have to sit underneath the molecule because there's no space above it. And so because the aluminium is sitting underneath the molecule and it's coordinating this sulfonate group, When you reach the point of acidic workup, protonation is going to occur above the sulfonate because below is going to be blocked by this reagent. So effectively, this silated oxygen here governs incorporation of this R group, cis to it. If we imagine an aluminium sitting here between them, that aluminium also causes the second aluminium to sit below it and opening the way for protonation above, thereby transmitting chiral information to the next two positions on the molecule. So to summarise, chemical reactions are governed by three things: steric, electronic and stereoelectronic bonding trends. Typically the stereoelectronic factors are overlooked when teaching organic chemistry, but they're really important for showing why stereoselective reactions occur and for explaining pericyclic reactions. Typically, reactivity is not down to a single one of these trends, but more like a concerted combination of all three, which makes understanding all of them really important. That's all for today. Thanks for watching. As always, leave a comment if this has helped you out.